So, hi everyone. This video is on solving a few problems from Terence Dow's book, and hopefully it will be helpful in practicing proofs and in writing proofs carefully. So first, I want to discuss the problem 1.34 from Terence Dow's book. It asks you to prove a part of another theorem, and this theorem states that if I have a subset of X, and X is a metric space, then being closed in the subset topology, subset of Y, is equivalent to there existing a subset of X such that it can be represented as K intersect Y, and so that this subset in the bigger space is closed. So closed subsets in the subset metric are actually closed intersections of closed subsets of the big space. Whenever you're proving something, you have to state the definitions clearly. So, and I would recommend doing so by adding, before you even start a proof or before you start solving a proof-based problem, the definitions that you will be using. This helps you focus on what are crucial. It gives you a visual cues of what kind of conditions you need to verify, and it will give you guidance on how to structure the proof as well. Now, the first definition is a subset is closed. Well, a subset is closed if you have any sequence in X, any element in X such that the sequence converges in X. So if this assumption implies that the element the limit point has to actually be in X. So this is an implication. Whenever you have an implication, you have to prove it by starting from the assumption and getting to the conclusion. So this will help you, writing this out helps you see that this will be part of the structure of the proof. Now, we have another concept here, that of relative topology. Now, if we have Y subset of X, the metric that we define on that subset, sometimes denoted dy or sometimes d dash y, is defined as just the original metric from X. But the domain is changed, domain in XY. Now, any definition that we have in Y means that it is defined relative to the distance in Y. Now, okay, we have collected the relevant definitions. You could add more. You could add the definition of D being a metric on X. But since this is a fairly familiar and simpler notion, we choose not to define it here rigorously. We will assume that the reader will know what the metric is, and if we use the properties of the metric, we will highlight them in the proof. Now, but what I now want to focus on is the nature of the statement that you're proving. And the nature here is an if and only if statement. That means there's two conditions here. We want to show that 1 implies 2 and 2 implies 1. That is how you prove an equivalency. So to do that, it consists of two directions. Now, one direction is 2 implies 1, and the other direction is 1 implies 2. And now, when you start proving an implication, essentially your first sentence should usually just be a reiteration of what your starting point is. This is important in terms of clearing out what the assumptions are. It also just orients the reader in knowing what you're doing. Of course, the reader could just scroll back up to this theorem statement, but to make it easier for him and to make it clear that you know what you're doing, you state clearly what is your starting point. So in this case, we start from the assumption that is assumptions of 2. So there we have, the setting is we have some subset E of Y. We have some subset K of X such that K is closed and K intersect Y is equal to E. So this is our assumption, and our ultimate goal is to now, using logic, get to the point where we have 1, namely that E is closed in Y. This is the statement of 1. And you don't have to do that, but it's good practice to keep the reader in line, online of what you're actually doing. So I had a statement here saying that, a subtitle here saying that proof that E is closed in Y, because that is what we're next doing. And the reader will then realize that, okay, we're proving that implication, we're trying to get to the conclusion. And where it helps the reader is in making sense of what we state next, because we're proving that E is closed. And that statement itself is an implication. It's an implication where we have an assumption and a conclusion. Just like here, we had an assumption and a conclusion. So we have another implication within this proof. And what that means is that, okay, when we're starting this proof, we have to again make the reader clear what is our assumption. Now the assumption is the assumption of being closed. The assumptions in the proof of being closed. So we have an X, we have a sequence, and we have that sequence converges. So in order to prove that E is a closed set in Y, we take an arbitrary sequence Xn that is in our set. We take a point in Y with the property that Xn is converging to X. And why I write this in such a verbose way is that if this was a published paper, you would have to write full sentences. And by writing full sentences, you guarantee that the reader is completely clear, knows what you have written. If I just were to write formulas like this one, and this one, it might leave some ambiguity about quantifiers. But here, the quantifiers are implied in the statement. For example, arbitrary means that this is for all quantifiers that we have opened. For every sequence, for every X and Y, the arbitrary quantifier is there. Okay, so now we've stated our assumption and we start by getting to the conclusion, but we cannot get to the conclusion that X is in our set A immediately. We have to use our assumptions somehow. So we start by using the assumptions. And a good standard way of using assumptions is that you make it clear which assumption you're using. So because K intersect Y is E, this means that the sequence of points that are in E is also a sequence of points in K. So this combines what assumption we are using. We stated that assumption here, so we can use it now. And it tells us what is the conclusion. Now, okay, since Y is a subset of X, then this limit point that was in Y will also be in X. Okay, great. So now we have a sequence in K and a sequence of points in X. And why did we do that? Well, we wanted to apply the definition of being closed, which we had stated as an assumption here, again. So K is closed. Now you have a sequence of points that we know is in K. what we can then conclude is that the limit point is also in K. So again, we made clear which assumption we're using and what we're doing with it. So we're concluding that this limit point X is in K. But now, X is in Y, because we assumed that. X is in K, because we just concluded that. So it's in both of them. So it's in the intersection, Y intersect K, which was by definition E. So we get that X is in E, which was exactly what we wanted to prove, and therefore E is closed. Now, this ending statement E is closed is because we proved this for everything that satisfied the assumption. So we concluded from everything that X was also in E. Therefore, this proof applies to all and proves this implication. Now the other direction, from 1 to 2. Again, we start from clearly stating what is our assumption. Suppose E is closed in Y, in the subset metric of Y. And we want to conclude that there exists this subset K, whose intersection is E. And this K should be closed. Well, when you're proving that something exists, you have to describe how to choose it or why it exists. In this case, we choose K equals the closure of E in X. If you're watching this video before you've watched the Monday lecture, I define the closure in the Monday lecture today. So we choose this as a set. And this closure, it could be defined either in Y or in X, as we talked. Context, and I've talked with many people, context matters in the metric space. We have to tell where is the closure done. So we do the closure in X. So by theorem, and so, okay, this is now a set. We have to prove now that K is closed and that K intersect Y is X. Okay, so by theorem, the closure is closed. Okay, so we can certainly quote some facts that are very standard, and this is one of those facts that we will prove today in lecture, so that is allowed. Okay, so K is closed, but now we have to prove that K intersected with Y is E. So let's again make one of these boxes to tell the reader what we are, or a subtitle, what we're wanting to do. Prove that K intersect Y is equal to E. Okay. Proof of this. Well, E is a subset. Now we're showing the two sets are equal. So again, we have to prove two inclusions. So we start, there will be two parts. First is E is subset of that intersection. So E is a subset of E bar. So we start from something that is true. So therefore, E intersected with Y is a subset of E bar intersected with Y. But then E intersected, but E is also a subset of Y. So intersected Y is equal to E is a subset of K intersected Y because K is equal to E bar. Okay, so we get that E is a subset of this, essentially for free. Now the other direction. So for the other inclusion, take x inside k intersect y, and we want to conclude that this is also an element of E. Well, x belongs to k, so x belongs to E bar. So for every radius positive, BXR intersected with E is not empty. Again, we could quote a theorem here, but let's recall this step. Let's open up this step. Choosing R equals 1 over n for any n in natural numbers, we can find a sequence such that xn is in Bx 1 over n intersected with E. Because this set is not empty, we can find a sequence. So by following immediately the statement with this, we see that this is possible. Okay, so we have a sequence xn. Now, limit n goes to infinity, xn is equal to x is easy to see, since limit n goes to since the distance xn to x is at most 1 over n and is bigger than or equal to 0. So limit n goes to infinity, distance xn to x is equal to 0. And this is the definition of convergence. So we get that xn converges to x, and xn are all elements in E, which is a subset of y. So xn is in y. Yeah, xn is in y, and x is in y, since x belong to x intersected, or k intersected with y. So now we have a sequence of points in E that converges to a point in y, but E is closed in y. So by definition, x also belongs to E, but this is exactly what we wanted to conclude. Therefore, E is a subset of k intersect y, and this concludes the proof. Now there is a small detail here in the middle that I would like to highlight in terms of proof techniques. Now, from this fact that you have constructed in this 1 over n ball a sequence of points, this conclusion is always the same. So you could opt out from not saying it, but for now, say it, just so that it's clear to the grader and to me that you actually know what you're talking about. Okay,